Hi, welcome to this lecture on control flow. So far we've discussed Python programs which are called straight line programs. So these programs are executed start to end, one statement at a time, and these programs don't involve branching or looping. But what if you want to write a program where you perform a certain task under some condition and some other task under a different condition? For that, we need to be able to branch inside of our code. And then what if you want to write a program where you perform a certain task many times? For that, we need to be able to loop inside of our program. So in this lecture, what we're going to do is we're going to talk about conditional statements, such as an if statement, and then we will talk about loop statements, such as while statement and for statement, and then we will discuss how you nest one statement inside of another, and then we will talk about several applications where we make use of conditional and loop statements, and then we will discuss some special conditional and loop constructs. Now, applications typically require different actions to be performed for different inputs. And one way to express these differences in Python is using a conditional statement such as the if statement. Okay, so here is the most general syntax for an if statement in Python. You have the keyword if, followed by a Boolean expression, followed by a colon, and then you have a block of statements. Okay, and a block is specified in Python by indenting the statements by some number of spaces. Okay, so all these statements, they make up a block. And then you have another keyword, elif, which stands for else if, and a Boolean expression, and then colon, and another block of statements. Okay, and then you have else if again, a Boolean expression, colon, and another block of statements, and so on and so on. So you can have any number of these else if clauses. And finally, you have an optional else clause. So that's the keyword else with colon, so there's no Boolean expression here. Okay? And then a block of statements. So that's the most general syntax for an if statement. You have the if clause, any number of else if clauses, and then finally an optional else clause. So that's the syntax. Now the question is, what is the semantics, or how is this statement executed at runtime? How does it behave at runtime? Well, here is how it works. So the Boolean expression is evaluated first. Okay, and if that expression happens to be true at runtime, then all these statements are executed in sequence, one after the other. Okay, and once that is done, control is transferred to the end of the statement. So you're out of the if statement. Okay, but what if that Boolean expression was not true? Well, in that case, this Boolean expression is evaluated, and if that happens to be true, all these statements are executed in sequence, and control is transferred to the end of the if statement. So you're out of the statement. Okay, but what if this Boolean expression was not true? Well, in that case, this one is evaluated, and if that happens to be true, all these statements are executed in sequence, and you're out of the loop. Okay. Now, what if none of these Boolean expressions are true? Well, in that case, if there is an optional else clause, then all these statements are evaluated unconditionally. Okay, so if none of these Boolean expressions are true, then these statements inside of the else clause, if there is one, gets executed in sequence. So that's basically how an if statement works in Python. Okay. Now let's look at a concrete example where we make use of an if statement. This program is called flip.py, and what it does is it simulates a coin flip, okay, a fair coin flip, and the program is going to write either heads or tails to standard output to the terminal. Okay, so it's going to simulate the flip of a fair coin, and it's going to write either heads or tails. So that's what the program does. So let's see how it's implemented. So we import the module random, Well, we need random because we are simulating a random process such as a coin flip. Okay? So we need that module. And then we also need stdio because we're going to write something to standard output. Okay, the program is extremely simple. We make use of an if statement which works as follows. So for the Boolean expression, for the if statement, what we have is what you see here. We make a call to the rand range function from the random module, giving it two numbers, 0 and 2. Now, if you recall, the way rand range works is it returns a random integer between a and b, where a is the first argument, in this case 0, and b is the second argument, in this case 2. But remember that a is inclusive whereas b is not inclusive. Okay, so since a is 0 and b is 2, rand range is going to return either 0 or 1 with probability half. Okay, so it's going to return 0 with probability half and 1 with probability half. Okay, now if the value that is returned by rand range happens to be 0 at runtime, what we do is we treat it as heads, and in that case we end up writing the string heads to the terminal. And once that is done, we are outside the if statement, and we are also done with the program because there is nothing after the if statement. But what if rand range returned not 0 but 1? Well, in that case, this part of the expression is 1. 1 is not equal to 0, so the Boolean expression is false, in which case it is this statement that gets executed, and that ends up printing the string tails to the terminal. And we are done with the if statement as well as the program because there is nothing after the if statement. Okay, so as you can see, the program correctly simulates a coin flip. Okay, so with probability half, it's going to print heads, and with probability half, it's going to print tails. Let's see how it behaves when you run the program. So we run it by saying python3 flip.py, and the program comes back with the output tails. Then I run it again, it comes back with the output heads. I run it again, comes back heads, run it again, comes back tails, run it again, it comes back heads. So if you run this program, let's say 100 times, roughly 50 times you're going to get heads, and the remaining times you're going to get the output tails. All right, so that's an example where we made use of the if statement, a conditional statement, to do something interesting, such as simulating a coin flip. Okay. So now let's talk about loop constructs. Now, many computations are inherently repetitive, meaning you want to perform a certain task many times. And the basic Python construct that you use for handling such repetitive computations is the while statement. Okay? And here's the most general syntax for a while statement. You have the keyword while, followed by a Boolean expression, followed by a colon, and then you have a block of statements, right? Again, remember that a block is signified or denoted by indentation, right? So you have all these statements that make up the block indented by some number of spaces. Okay, so in Python, a block is denoted by indentation. Okay, so that's the syntax for a while statement. What's the semantics? How does it behave at runtime? Well, here's how it works. So it's the Boolean expression that's evaluated first, and if it happens to be true, then all these statements get executed in sequence once. Okay, and then what happens is the Boolean expression is evaluated again. If it is still true, the statements are executed once more, and then the Boolean expression is evaluated again, and if it's still true, the statements are executed once more in sequence, and so on and so on and so on. And at some point, one of these statements is going to falsify this Boolean expression, so it would evaluate to false, and when that is the case, you're out of the while loop, okay, to whatever follows the while loop. So typically when you write a loop, you need to make sure that this Boolean expression is at some point falsified. right? If you don't, then you're stuck in an infinite loop, right? So you typically write a while loop where one of these statements ends up falsifying the Boolean expression and you're outside the while loop, right? Okay. But I must mention here that it's not that, while loops must always terminate. So we'll see examples later on where you write a while loop that runs forever, okay? Meaning the Boolean expression is never false. Okay, so that's a while statement. Let's look at an example of a program where we make use of a while statement. So this program is called 10hellos.py. And what it does is it simply writes 10 hellos to standard output or the terminal. Okay, and let me show you the output. So if you say Python 3 10hellos.py, which is how you run this program, the program comes back with this output: first hello, second hello, third hello, and so on. So this is the output that we want to produce. Okay, all the way up to 10th hello. So how do we do this? Well, the program is rather simple. We import the stdio module because we want to write some output to the terminal, and then what we do is we make 3 calls to write ln to write out the first 3 hellos. Okay, so we write first hello with a new line character, second hello with a new line character, and third hello with a new line character. Okay, and then we make use of a while loop to write the remaining 7 hellos. Okay. Now, why do we handle the first 3 hellos differently outside of a while loop? Well, that is because the prefix is quite different for the first 3 hellos. Okay, so for the first hello, it is 1 followed by st. For the second, it is 2 followed by nd, and then for the third one, it is 3 followed by rd. Whereas starting with the 4th hello and all the way up to the 10th, the prefix is exactly the same: th, 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 and so on, all the way up to 10th hello. So that part can be nicely handled inside of a while loop, and which is what the program does. Okay, so it makes 3 calls to write ln to print the first 3 hellos, and then what it does is it sets up a variable called I with the value 4. Okay, why 4? Because that's the next hello that we want to print, the 4th hello. Okay, and then we make use of a while statement to print the remaining hellos, the remaining 7 hellos. So let's see how that works. So we say as long as this variable I has a value that is less than or equal to 10, so this is a Boolean expression. Okay, so as long as this expression is true, what we say is we write the value I as a string concatenated with the string th hello. Okay, so we take the current value of I, which to begin with is 4, turn it into a string, so that becomes the string 4, and then we concatenate that with th hello. So this is 4th hello, which is what gets printed, and that's what you see here. Okay, and then what we do is we take the current value of I, which is 4, add 1 to it, so this whole thing is 5, and we store that result into I, so I is now 5. That's the new value for I. And then how does the while loop work? Well, we check if the current value of I, which is now 5, is it less than or equal to 10? Well, it is. So this expression is still true, and what do we do in that case? Well, we convert 5, which is the current value of I, into a string, and then concatenate that with the string th hello, and that's what gets printed, which is this line of output. And then the current value of I, which is 5, is added to 1, which is 6, so this whole thing is 6, and that is now stored into I. Okay, so now the next time around, I is 6. Is it less than or equal to 10? Yes, so this Boolean expression is still true, and in that case we print 6th hello. Okay, and then I becomes 7. 7 is still less than or equal to 10, so we are going to print 7th hello. And then I becomes 8, we get 8th hello. I becomes 9, we get 9th hello. I becomes 10, we get 10th hello. And then something interesting happens. So the current value of I is 10, so this whole thing is 11, and that gets assigned to I. So we go back and evaluate the Boolean expression, but now you have 11 here. Is 11 less than or equal to 10? Well, no, so the Boolean expression is false, and you're out of the while loop, and you're done with the program as well. Okay? And the program has correctly produced that for output, 10 hellos. Okay? So that's how the program behaves. So let's look at a trace of this program and see how things unfold when you run the program. Okay. So what I'm showing you here is basically the trace of the single variable that you have inside of the program, which is I. Okay? And I is initially set to 4, and when the Boolean expression is evaluated, 4 is less than or equal to 10, so that's true. So we end up printing 4th hello. Okay, that's the output. And then I becomes 5. And then when the Boolean expression is evaluated, 5 is still less than or equal to 10. So we end up getting 5th hello for output. And I now becomes 6. And since 6 is less than or equal to 10, we end up getting 6th hello. I then becomes 7. 7 is less than or equal to 10. So we get 7th hello and I becomes 8. 8 is still less than or equal to 10. So the Boolean expression evaluates to true. We get 8th hello and I becomes 9. And then since 9 is less than or equal to 10, we get 9th hello and I becomes 10. And 10 is less than or equal to 10. So the Boolean expression is still true. So we get 10th hello and I becomes 11. But now 11 is not less than or equal to 10. Okay, so that's when the Boolean expression is false. You're outside of the while loop and you're done with the program. Okay, and so that's how you trace such a program. And it's always a good exercise to trace a program on small inputs for the different variables in the program. Okay, because when you do that, you understand exactly how the different constructs in the program behave at runtime. Okay. Let's look at another program where we make use of the while loop. This program is called powers_of2.py, and what it does is it takes a positive integer n as a command line argument, and it writes to standard output or the terminal a table that shows the first n powers of 2. Okay, so for example, if n is 3, then it's going to display a table that looks like this. It's going to display 0 and the power 2 to the 0, which is 1. And then it's going to display 1, 2 to the 1, which is 2. And then 2, 2 to the 2, which is 4. And then 3, and 2 to the power 3 is 8. Okay, so what the program does is it takes a number like this, a number n as input, and for output it produces this table which shows the n powers of 2. Okay, so that's the input and output for the program. So let's see how it's implemented. So we import our familiar modules, stdio for output and sys because we're going to read a command line argument. And then we get the first command line argument and turn it into an integer, store it in n. Right, so that's the input. And then we initialize two variables, power set to 1 and I set to 0. Okay. Now, power is always going to store the value 2 to the I. So keep that in mind. And I is initially 0. What is 2 to the 0? It's 1. So that's why power is 1. So power will always store the value 2 to the I. Okay. So now let's see how the program generates its output. So there is, it makes use of a while loop, and the Boolean expression says as long as I is less than or equal to n, so that's the Boolean expression, as long as I is less than or equal to n, we simply print out the current value of I as a string concatenated with a space and the value of power as a string. Okay, so the first time around I is 0, so we end up printing 0 space power, which is 1, so 0 space 1. Okay, and that's correct because 2 to the power 0 is 1, so we correctly end up printing 0 space 1, right? And then what we do is something very interesting. We update both power and I as shown here. So for power, we take the current value of the variable and simply multiply 2 to it and store the result back into power. So power was 1 to begin with. Now it's going to be 2 which gets assigned back to power. So the new value for power is 2. And then I is simply incremented by 1. So it was initially 0, it becomes 1, and that's assigned to I. So I, the new value for I is now 1. And in the next iteration, what we do is we check if 1 is less than or equal to n. And if so, we end up printing 1 space power. But what was the value of power? It was 2, which is basically 2 to the power 1. Okay, so that's what you get for output. And for the next iteration, power is now going to be 2 times 2, which is 4, and I is going to be 1 plus 1, which is 2. Okay, and so on and so on and so on. And at some point, I is going to exceed n, in which case this Boolean expression is false, and you're outside of the while loop, and you're done with the program. Okay, so that's how this program works. So let's look at some input and output. So here, we run the program powers of 2.py with the input n equals 8. And for output, it produces this table. So 0, 2 to the power 0, 1, 2 to the power 1, 2 to the power 2, which is 4, and so on and so on, all the way up to 8, 2 to the power 8, which is 256. Okay, so that's the output when n equals 8. So let's now trace this program just like what we did with the 10 hellos program. But in this case, the program has 2 variables, and we're going to trace the values of both the variables. And these variables are power and I. Okay? And remember that power is always going to be 2 to the I. And we're going to use n equals 8 for our trace. Okay, so let's see how this works. So we first check if I is less than or equal to 8. Well, 0 is clearly less than or equal to 8. So the Boolean expression is true, in which case what we do is we write 0 space 1 for output. That's this line, right? We write the value of I space the value of power, which is 0 space 1. And then I is incremented by 1, so I is now 1, and power is 2 times the current value. Well, the current value is 1, 2 times that value is 2. Okay, and then we check, is the Boolean expression in the while loop still true? Well, 2 is still less than or equal to 8, so we end up printing the current value of I space power. So it is 2 space 4. All right. And then what we do is we increment I by 1, so I now becomes 3, and then power is simply the current value 4 times 2, which is 8. Right? Now is 3 less than or equal to 8? It is, so we end up printing 3 space 8 for output, right? Which is basically I space power. And then I is incremented by 1, so I becomes 4. Power, the current value is multiplied by 2, so the new value for power is now 16. And then we check, is 4 less than or equal to 8? It still is, so we end up printing I space power, which is 4 space 16, and then I is incremented by 1 to 5. Power is doubled, so it's now 32, and then is 5 less than or equal to 8? It is, so we end up printing I space power, which is 5 space 32. I becomes 6, power becomes 64, twice the current value, and then I is still less than or equal to 8, so we end up printing I space power, which is 6 space 64. I becomes 7, power becomes twice the current value, which is 128. 7 is still less than or equal to 8. We get this for output. I becomes 8, and then power becomes 256, twice the current value. 8 is still less than or equal to 8, so we end up printing 8 space 256, right? And then I becomes 9, but now what happens to the Boolean expression? Well, 9 is not less than or equal to 8, right? So the Boolean expression is false, and you're outside the while loop, okay, and you're also done with the program. So that's how we correctly end up generating this output. Okay, so again, it's very, very instructive to trace a program for small values of the variables in the program. All right, because then you know exactly what's going on. Okay, now typically inside of your program, you modify the value of a variable quite often. Okay, and as a result, Python provides a shorthand notation for that purpose, for modifying a variable. Okay, and the most common shorthand notation is abbreviating this guy here, I equals I plus 1, with this guy here, I plus equals 1. So notice that here what we're doing is we're taking the current value of I, adding 1 to it, and storing the result back into I. Now how many characters is this statement? Well, it's 5 characters. And the corresponding shorthand notation is this one, but the shorthand notation only has 4 characters. Okay, but other than that, it has exactly the same meaning. So these two guys are absolutely equivalent. Right? So in your code, if you want to update, if you want to increment I by 1, you can either do it this way by saying I equals I plus 1, or you can use the shorthand notation and say I plus equals 1. Both mean exactly the same thing. Okay. Now the same notation is also available for other binary operators such as subtraction, multiplication, and division. So for example, if I is 3, you could do something like I star equals 3, okay, which is the same thing as saying I equals I times 3. So these two things are absolutely equivalent. This one just has 4 characters. That's the shorthand for this one. So what is the end result? What is the new value for I? Well, you take the current value, which is 3, multiply that by 3, 9, store the result back into I. So I in both cases is 9 now. So you can use this form, which is the shorthand form, or this form, right? Now, the scope of a variable is the part of the program where it is defined, meaning it's the set of statements that follow the definition in the same block. And recall that block is denoted by indentation level in Python. So what we are saying here is if you have, let's say, a while loop, okay, some expression, and then you have a bunch of statements here, okay, which make up the body of the while loop. Now the question is, let's say I define a variable called x set to the value 5. So what is the scope of this variable x? Meaning, what are all the different places where I can access x? Well, what we're saying here is that the scope of x is basically all the statements that follow that definition in the same block. All right, so you cannot access, so it is wrong to say write ln x over here outside the while loop, because x is simply not visible here. All right, so that's what we mean by the scope of a variable. So the scope of x is just this block. All right, but what if I have a variable here that says y equals 15? What's the scope of y? Well, y is visible here inside of the while loop, and it's also visible outside the while loop because its scope, it has a broader scope than x. Okay, so here I can certainly say write ln, I mean this is wrong, so write ln of x is wrong, but I can certainly say write ln of y. So this is okay. Okay, so y has a broader scope than x. Okay, so that's the notion of the scope of a variable. It's a very important idea. Now, there is another form of a loop statement that is available in Python, and that's the for statement. Okay, and the for statement, it turns out, it provides a more compact notation for carrying out repeated computations. All right, so at times it's more natural to use a for statement because it's more compact. But in terms of power, it is just as powerful as the while statement. Okay, they're both equally powerful, but at times it's more natural to use a for statement over a while statement. So here is the most general syntax for a for statement. You put the keyword for followed by some variable. You can call this variable whatever you want, and then the keyword in, and then what you do is you put what is called an iterable object. Okay, and I'll explain what that is. And then colon, so colon is part of the syntax, and then you have a block of statements which form the body of the for statement. And notice that all these statements are indented by some level. Okay, so that's the syntax. Now let's talk about this iterable object. So the most commonly used iterable objects are lists that contain what are called arithmetic progressions of integers. Okay, so here for an iterable object you typically put a list of an arithmetic progression. Now what is an arithmetic progression? Well, here is an arithmetic progression. We start with some number, let's say 5, and then go 7, 9, 11, and so on, all the way up to let's say 17. Okay, so this is an example of an arithmetic progression that starts at the number 5 and ends at the number 17 and has a common difference of 2. Okay, so 5 plus 2 is 7, 7 plus 2 is 9, and so on, right? And then finally 15 plus 2 is 17. So that's an example of an arithmetic progression that you could put here. Now, when you do that, when you have, let's say, exactly this progression here, how does this for statement work? Well, this variable that you put here, let's even call it x. So this variable will initially take on the value 5. Okay, and then you perform, you execute all these statements in sequence, and then the next time around the variable x will take on the value 7, and you repeat these statements again in sequence, and then x takes on 9, and then you repeat the statements, and so on and so on, and at the end x is going to take on the value 17, and all these statements are executed in order, and then the for loop is done because it has exhausted this arithmetic progression. Okay, so that's how the for loop works. Let's take another example. Let's say this iterable object was a different arithmetic progression. So this time around, let's say it is 1, 2, 3, 4, and 5. Okay, and let's say this variable is called x. So in the first iteration, x is going to take on the value 1. All these statements are executed, and then x becomes 2. All these statements are executed a second time. X becomes 3. One more time, x equals 4. All the statements executed one more time, and x equals 5. All the statements executed one more time, and then that's it. So now the arithmetic progression is exhausted. Okay? So that's how the for statement works. Now the question is, how do you build these arithmetic progressions? Well, that's where you make use of this built-in function called range. All right, so range is a built-in function, meaning it comes for free. You don't have to import it. So how does range work? Well, range takes these arguments: a start argument, a stop argument, and an optional step. And what it returns is a list that contains an arithmetic progression that starts at this number given by start, and it ends just before this number stop, the second argument. And what we mean by just before is that stop is not inclusive. All right, and then the progression is either in increments or decrements given by the optional step argument, okay, which defaults to 1. So if you don't specify a step, then the step defaults to 1. But if you specify a step, and if the step is positive, then the progression is incremented in that step, and if that step is negative, it is decremented using that step value. All right, so let me repeat. So range returns a list that contains an arithmetic progression of numbers that starts at start, ends just before stop, meaning stop is not inclusive, and it is in increments or decrements depending on the size of step, which defaults to 1 if the step is not specified. Okay. So let's look at some example of calls to range. But before that, I should mention that range can also be called just with one argument. And when you do that, that argument is interpreted as the stop value, right? And the start is set to simply a 0. So range of just one number is equivalent to saying range of 0 stop, right? Because the start defaults to 0 in that case. And of course the step is 1, because we didn't specify a step explicitly. So step defaults to 1 by this rule. Okay. So now let's look at some concrete examples. So if we say range 8, 0, minus 2, what is start? Well, start is 8. What is stop? 0. What is the step? It's minus 2. So it's a decrement, right? So this results in an arithmetic progression that starts at 8 and it's constantly decremented by 2. So the next value is 6 because it's 8 minus 2. The next value is 4, which is 6 minus 2. And then the next value is 2, which is 4 minus 2. And notice that the stop value was not included. Okay, so the progression stops just before the stop value, and that's what we said here. Okay, so that's one example. Here's another example, range 3, 9. So when you call it like that, without a third argument, 3 is the start, 9 is the stop for the arithmetic progression. So this corresponds to the progression that starts at 3, and because there was no step argument, the step is 1 by default. So the next value is 4, next value is 5, next value is 6, next value is 7, next value 8, and that's it. We stop there because the end value is not inclusive. Here's another example. We make a call to range just with one argument. So that is like this guy here. So stop is 5 now, but this then is the same as saying range of 0 and 5. But what is that progression? That is exactly what is given here. The start value is 0, stop value is 5, increment or step is 1, right? So the progression is 0, 1, 2, 3, 4. Notice that the stop value is not inclusive. Okay, so these are some examples of calls to range, and whatever range ends up returning is something that you can put here inside of a for statement. So let's now look at an example where we make use of the for statement. So we're going to revisit the 10 hellos program, and we're going to write it now using a for statement. So our previous implementation was using a while statement, but now we're going to write 10 hellos with a for statement. It's much easier doing it with a for, right? So here is the code. We first import stdio, and then just like what we did in the previous case, we simply write the first 3 hellos directly by making calls to write ln. So write ln first hello, write ln second hello, and write ln third hello. And then for the remaining 7 hellos, we set up a for loop where we say for I, so this is so the variable now is called I, in keyword range. So this is now an iterable object. So we are making a call to range to get a particular progression, arithmetic progression, where the start value is 4, stop value is 11, and the step defaults to 1 because we didn't explicitly specify. So what is this arithmetic progression? Well, it is 4, 5, 6, 7, 8, 9, and 10. We stop at 10 because stop is not inclusive. Okay, so that's the arithmetic progression. And how does the for loop work? Well, in the first iteration, I takes on the value 4, and you execute the body of the for statement. So we simply say 4 as a string concatenated with th hello. So this is going to print 4th hello. The next time around, I is going to take on the value 5, and 5 as a string is concatenated with th hello. So that's 5th hello that gets printed. Then I becomes 6, we get 6th hello. I becomes 7, we get 7th hello for output. And then I becomes 8, we get 8th hello. I becomes 9, we get 9th hello. I becomes 10, we get 10th hello. And then that's it. The progression is exhausted, so the for loop is done. And we are outside of the for loop and done with the program. Okay, so this program where we have made use of a for statement instead of a while statement does exactly what 10 hellos is supposed to do, meaning print the first 10 hellos to the terminal. Okay. Okay, now strings which are nothing but sequences of characters. They are also iterable objects. Okay, so strings are iterable in Python. So what it means is you can stick a string in a for statement. So you can say something like for I in some string like Alice, and then you do something. Okay. And the way things work when you have a string here for an iterable object is that I first takes on this value, the first character in the string, and then you do the body. And then I takes on the second character in the string as its value, you execute the body again, and so on and so on and so on. Right? And then finally I takes on the value E, you execute the body once more, and you're done with the for loop. Okay? So when you use a string in the place of an iterable object in a for loop, then you're basically enumerating the characters in the string, right? And here's a concrete example of that. We import stdio, and then we say for C, which is the variable name, you can call it whatever you want, we call it C, in the string agct, okay? And then for the body, what we say is stdio.writeln C. So how does this thing work at runtime? Well, in the first iteration, C is going to take on the value A, and A gets written. That's how you get this output. And then in the next iteration, C takes on the value G, and G gets written up. In the next iteration, C takes on the value capital C gets written up. Right? And then finally, C takes on the value capital T, and then the writeln prints T out. Okay. So you can use a for statement to very nicely, very easily enumerate the characters in a string. All right? Okay, now let's talk about the concept of nesting. The if, while, and for statements that we've seen so far are collectively called the control flow statements. Okay? And they have the same status as some of the statements that we've seen before, such as assignment statement and so on, right? And as a result, what you can do is you can use a control flow statement whenever a statement is called for. Okay, so a control flow statement has exactly the same sort of like status as assignment statements or any other statement form in Python. Okay, so wherever a statement is called for, you can use a control flow statement such as an if statement or a while statement or a for statement. And in particular, what you can do is you can nest one or more of the control flow statements in the body of another. Okay, so for example, you can have a while statement inside of an if statement. That's perfectly legal. You can have a for inside of a while. You can have a while inside of a while, and so on and so on. You can have an if inside of a for. Okay. So the bottom line is that we can nest one or more of the control flow statements in the body of another. All right. And we'll shortly look at an example of this. Okay, so this program is called Divisor Pattern.py, and what it does is it accepts an integer command line argument n, so that's our input, and then what it does for output is it writes to the terminal an n by n table or an n by n matrix, and each cell in the table is going to be an asterisk, or it's going to be a space, right? Just a blank. And it's going to be an asterisk when the corresponding row number I of that cell divides the corresponding column number j. Okay, or vice versa, or the corresponding column number divides the corresponding row number. Okay, so that's when you see an asterisk for output at a particular cell ij. But if neither the row number divides the column number or the column number divides the row number, then what you have in that cell is simply a blank. Okay. So let me explain this again. So what you're going to get for output is an n by n table or a matrix, right? So for example, 4 by 4. Right? And if you go to a particular row, let's say I, and a particular column, let's say J. At this cell, you're either going to have a star or a blank. And you see a star when I divides J or J divides I, meaning this number divides that number or that divides this. In that case, you see a star. And you see a space when that is not the case, meaning neither I divides J nor J divides I. Okay? So let me give you a concrete example of input and output. So if we run this program divisor pattern.py with the input 3, then we get a 3 by 3 table. Okay, and these are the values in the cells. Okay, so let's put some column numbers. So these guys are row numbers. So this is like your I, and we can even put column numbers. So we say 1, 2, and 3, and this is like your J. Now, why is it that we see a star here? Well, the corresponding row number is 2 and the column number is 2. Well, does 2 divide 2? Yes, so we have an asterisk. Okay, so in order to have an asterisk, either I has to divide J or J has to divide I. Okay, that's all that it takes. Let's take another example. Why do we see a star here? Well, what is the corresponding row number? I is 1. What's the corresponding column number? Well, it's 3, right? J is 3. Does 1 divide 3? Absolutely. So we have a star there. What about this star here? Well, for this guy, I is 3 and J is 1. Does 3 divide 1? No, it does not. But does 1 divide 3? Yes. So we have a star. So all that it takes for a star is either I divides J or J divides I. Okay. What about this cell here? Why is it a blank? Why is it a blank? Well, I is 2 for that guy and J is 3. Okay. Does 2 divide 3 or 3 divide 2? No. So we have a blank, right? So that's how you get this output. Okay. And here is the output for n equals 10. So you get a 10 by 10 table, and each cell is either a star or a space. And it's a star when I evenly divides J or J evenly divides I, and it's a space when that's not the case. Okay. So now let's look at the program itself. So we import our usual modules, stdio and sys, and then we get a single command line argument n as an integer. And then we have an example of nesting. So we have one for loop nested inside of another. Okay. So we say for I in range 1 through n plus 1, all right, and for each such I, J goes from 1 through n plus 1, all right. So for example, if n is set to 3, then what is going to be this iterable object, this arithmetic progression? Well, it's the range of 1, 4, but what is range of 1, 4? Well, it is the progression 1, 2, and 3. 4 is not inclusive. And for each such I, J is going to be also the progression given by range 1, 4, because 1, n is 3, so n plus 1 is 4. So this is exactly the same progression, 1, 2, 3. Okay. So I takes on values 1, 2, and 3, and for each such I, J takes on values 1, 2, 3. Okay, because J loop is nested inside of I loop. Okay, and then what we do here is we have an if statement inside of the inner for loop where we implement this idea. We check if I, if J evenly divides I. So if J evenly divides I, this is going to be true. So this is a Boolean expression. Or I evenly divides J. This is also a Boolean expression. So we are checking if J divides I or I divides J. And if so, we write a star followed by a space and without a new line character at the end. Right? And that's exactly what we want. When I divides J or J divides I, we write a star followed by a space. Otherwise, we simply write two spaces. Okay, again without a new line character. So that's what we do. Now notice here, outside of the inner loop, but inside of the outer loop, we simply write the value of I, but we write it with a new line character at the end. What are we doing here? This is what is responsible for writing these row numbers. All right. So once the J loop is done, we have processed all the columns for a particular row, right? And that's exactly when we want to write the row number at the end of each row. Okay. So we simply write the row number, which is simply given by the value of I. Right? And then we proceed to the next value of I and carry out this computation again. Right? So that's how things work. Now let's trace this program for a small value of input, namely n equals 3. And the two variables that we're going to trace are I and j, the loop variables. Okay, so this guy and this guy. Now, remember that when n is 3, I is going to take on values from the progression 1, 2, 3, which is what we just talked about. And then j is going to take on values from 1, 2, 3. Okay? For each I, j is going to take on values 1, 2, 3. And I itself is going to take on values 1, 2, 3. Okay, so the very first time in, I is 1 and j is 1. Okay, I is 1 and j is 1. Well, does 1 divide 1? Yes, so this part is true. We don't even have to check for that. The whole Boolean expression is true. So we end up writing star space. All right, so that's what we're doing here. And that's how we get this output. Okay, and then I remains at 1, but j now takes the second value in the progression, which is 2. So I is 1 and j is 2. Well, does 2 evenly divide 1? No. Does 1 evenly divide 2? Yes. So this part is true, so the whole thing is true because of a logical OR. So we end up writing star space, and that's how you get this output. Okay? And then I remains at 1 and j becomes 3, the last value in that progression. Okay? And and we check again. Does 3 divide 1? No, but 1 surely divides 3. So the Boolean expression is still true. We write a star and a space. That's how we get this output. Right? We get this much, the output. And then the J loop is done because the progression is exhausted. So now we are here at this line, and what do we do here? We simply write the value of I, which was 1, followed by a new line character. So that's how we get I, and we are on a new line now to write the next line. Okay? Now what? So now I takes on the second value in its progression, which is 2. Okay? And j goes back to 1. And that's what we have here. And does 1 divide 2? Yes, so the whole Boolean expression is true. We write a star space. So that's how we get that output. And then I remains at 2. J now becomes 2. Now does 2 divide 2? Yes, so we get this much of the output, this part. And then j becomes 3 and I remains at 2. So now does 3 divide 2 or 2 divide 3? No. So now we are here in the else clause because the Boolean expression was false. So what do? We write 2 spaces. So that's how you get these 2 spaces, all right? And now the J loop is exhausted, so we end up writing the value of I with a new line character. What was the value of I? It was 2. So we simply write 2 with a new line character. So we get that, and we are on a new line. And now I takes on the last value in its progression, which is 3, and j goes back to 1. Does 1 divide 3? Yes, so we get this much of the output. J now becomes 2, I remains at 3. Does 2 divide 3 or 3 divide 2? No, so we have 2 spaces for output. And then I remains at 3 and j becomes 3. Does 3 divide 3? Yes, so we get star space. Okay. So we are done with the inner loop. So j has exhausted its progression. So we are here. and we end up writing the value of I, which is 3, with a new line at the end. So that's how we get 3, and we are on a new line. But now notice that even the outer loop is exhausted. Okay, so we are done with the outer loop, and we are done with the program as well, right? And what we end up having here then is simply the prompt back. Okay, so that's how the program unfolds when you run it with the input n equals 3. So now let's look at some concrete applications where we make use of the conditional statement and the loop statements, right? So the first example that we're going to consider is this program called harmonic.py, and what it does is it accepts a single command line argument n as an integer, and for output it writes what is called the nth harmonic number, denoted by h sub n, right? And h sub n is simply calculated as the sum that is shown here. It is 1 plus 1 over 2 plus 1 over 3 and so on, all the way up to 1 over n. So for example, the first harmonic number h sub 1 is simply 1. The second harmonic number is 1 plus a half, which is 1.5, and so on and so on and so on. Right? So that's how the nth harmonic number is defined. Now, for those of you who are mathematically minded, you may want to note that the nth harmonic number is basically an approximation of the natural logarithm of n. Right? So it's h sub n is approximately log of n plus this constant for large values of n. Right? Okay, so now let's see how the program works. How does it compute the nth harmonic number? So it's fairly straightforward. We import a couple of modules, the usual ones, stdio and sys, and then we get a single command line argument as an integer, and we store it in a variable n. And then what we do is we initialize a variable called total to the value 0. So total is what is going to store the value of the nth harmonic number. And then we set up a simple loop where the loop variable I goes from 1 all the way up to n plus 1, right? In increments of 1, because we didn't specify the third argument to range. So for example, if n is, let's say, 3, then this arithmetic progression is going to be 1, 2, and 3. Okay, because 4 is not going to be included. Okay. And then what we do is, for each value of I, we simply take the current value of total and add to it 1 divided by I and store that as the new value of total. Now notice that we are using the shorthand notation here. So this line is equivalent to saying total equals total plus 1 divided by I. Okay, so we simply take the value of 1 over I and add that to total, and the whole result is assigned back to total. Okay, so we keep doing this until I has exhausted this progression, and at the end, when the for loop is done, we simply print the value of total, which stores the nth harmonic number. All right, so that's how the program behaves. So if we run it with n equals 2, we get the output 1.5. If we run it with n equals 10, we get that as an output. If we run it with n equals 10,000, we get that as the 10,000th harmonic number. Okay, let's actually trace this program for a small value of input, such as n equals 2. Okay, so let's say n equals 2, and let's trace the values of the variables I and total. Okay, two variables of interest. So total is initialized to 0.0. That's this line here. Now since n is 2, what is going to be this progression? Well, it's going to be 1, range of 1, 3, but then 3 is not included, so we simply have the progression 1, 2, right? And the first iteration I is going to take on the value 1. So what do we do here? we simply calculate 1 divided by 1, which is 1, add that to total, which was 0, and store that back into total. So the new value for total is now 1.0. And then I take the second value in the progression, which is 2, and we simply calculate 1 over 2, which is a half, add that to the current value of total, which is 1.0, so we get 1.5. Okay, for the new value of total. And then I is done because it has exhausted its arithmetic progression, right? So we are outside the for loop and we end up printing the value of total, which is 1.5, and that indeed is the second harmonic number. Okay. All right, so that's our first application where we calculate the nth harmonic number. Our next application is called sqrt.py, and what this program does is it accepts a floating point number c as a command line argument and simply calculates the square root of c up to 15 decimal places and prints that result out. Right? So if c is 2, it's going to calculate the square root of 2 up to 15 decimal places as the output. Okay, and this program calculates the square root of a number using what is called Newton's method of successive approximation. Okay, and here is how it works. Now, what I'm showing you here is the curve x squared minus c. All right, so it's simply the function x squared minus c that is plotted here, which is a quadratic. All right, and what we are interested in is the value of x. So we are interested in the value of x such that x squared minus c equals 0, right? Because when we find such a value, we have found the square root of c, right? Because if x squared minus c is 0, this is the same thing as saying x squared equals c, which is the same thing as saying x equals the square root of c, right? So what we are after is a value of x, a value on the x-axis such that f of x vanishes, or x squared minus c is 0. And geometrically speaking, what is that value? Well, it is something like this point here, because at this point, right, the function vanishes. The value of f of x is 0. Okay, and that point, that value of x is essentially square root of c. Okay, because if I plug in square root of c in here, I simply get 0 for the value of the function. So what we are interested in is simply a value along the x-axis such that x squared minus c equals 0. So how is this calculated? Well, we use Newton's method of successive approximation, which works as follows. So we start with an initial guess for the square root. Okay, so we say that our initial guess is t, okay, which is this point here. So the coordinates of that point is simply t comma 0, and t is our initial guess for the square root. Okay. Now we project this point upwards and we look at this point. What is the coordinates of this point? Well, if this guy is t0, this one is the value of the function at that point, which is f of t. Sorry, that's not correct. So this is t0. So the coordinates of this point, well, the x coordinate is t, and the y coordinate is f of t. But what is f of t? It is t squared minus c. We just plug in x equals t right here. Okay, so the coordinates of this point is simply t comma t squared minus c. Okay, its x coordinate is t, the y coordinate is t squared minus c. Okay, now what we do is at this point, we draw a tangent to the curve, which is this line here, and see where it intersects the x-axis. So it intersects the x-axis at some point, okay, whose y coordinate is certainly 0. But what is the x coordinate of the point where the line meets the x-axis? Well, that is fairly easy to figure out, and I'll let you guys do that as an exercise. You simply figure out the equation for the line, for this tangent line, using the formula y equals mx plus c, and see where it intersects the x-axis. Right, and if you do that calculation, you'll see that the x coordinate of this point where the line meets the x-axis is simply c over t plus t divided by 2. All right, and the y coordinate is 0. And now what we do is we repeat this process. So we say that from the initial guess for the square root, we have improved on it. So this is now our new guess. And we repeat the process. So from here, project it upwards and draw a tangent line at that point and see where that line meets the x-axis. Okay, and figure out the coordinates of this point and 0, and so on and so on and so on. Right? That's why this method is called the method of successive approximation. You constantly repeat this process. You start with some guess and you improve on the guess. From t, you went to that. From that, you go to that, and so on and so on and so on. And you stop this process when you're close enough to the desired value. Okay, so when you're within what we call an epsilon neighborhood of the desired value, you stop the process and you say that I'm happy enough with the result. Okay, and you print that as the square root of c. Okay, so that's the math behind this program, and let's see how we implement it in Python. Okay, we import our usual modules std, io, and sys, and then we set this constant, this variable epsilon. Notice it's all caps, and that's the convention that we're going to follow for constant variables. And we simply set it to 1 times 10 to the power minus 15. Right? It's a tiny number, very small number, extremely close to 0. Okay, and it's we are using the scientific notation here, and this variable is a constant, meaning its value is not going to change throughout the program, and and it's this number 15 that's going to give us the square root of the number up to 15 decimal places. Okay, all right, and then what we do is we get a command line argument as a floating point number, and we assign it to the variable c, and that's the number for which we want the square root calculated. Okay, and then what we do is we start with an initial guess. So that's that t that you see here is our initial guess for the square root of a number, and we say that initially the square root is simply c. Our initial guess is the input number c, which is certainly not always correct, but that's okay. We're going to improve on that, right? So we start with an initial guess of t equals c, and then we say that as long as the absolute value of this quantity 1 minus c divided by t squared is strictly greater than epsilon, and what this condition means is that as long as your current guess for the square root is outside of this epsilon neighborhood, continue improving it. So that's what we are saying. So if this condition is true, it means that we are not inside of this epsilon box. Okay, so in that case what we do is we say the new value for t. So this we started here, the new value of t is simply c divided by the current value of t plus the current value of t, the whole thing divided by 2. So that's this formula that you see here. All right, so you take that, make it into that. Okay, so that's like your new t, and from that you get the next value of t using the very same formula. Okay, so that's what we're doing here. So we take the current value of t and we improve on it using this expression. Okay, and at some point what's going to happen is this quantity here is going to become less than or equal to epsilon, in which case we are outside the while loop and we print the current value of t, and that is going to be the square root of c up to 15 decimal places. Okay, and and we can check that when t is precisely the square root of 2, is precisely the square root of c, or very close to the square root of c, then what is t squared? Well, it's going to be very close to c or identically c. But so in that case, what is this quantity here? Well, it's extremely close to 1. In which case, what is this quantity here? It is extremely close to 0, which means that is going to be less than epsilon, right? Because epsilon, though a very small number, it is greater than 0. But once this guy is very close to 0, it can become less than epsilon, in which case you're outside the while loop, right? And you end up printing the current value of t, which is the square root of c. Okay, so we run the program as such, giving it a value for c. So if we say c equals 2, the program comes back with the square root of 2 up to 15 decimal places, right? So that's that. And then we give another number for c, and the program comes back with the square root of that number. Okay. So this is also a very nice application where we make use of a loop statement to solve a very interesting problem, such as figuring out the square root of a number. The next application is called binary.py, and what it does is it takes an integer n as command line argument, and it simply writes the binary representation of that number to the terminal. Okay, and we all know, how to turn an integer into the corresponding binary representation. I mean, this is something that we talked about in the section that was titled Building a Computer, right? So here is a Python program that will actually do that for you. It would take an input, an integer n, and write the corresponding binary representation. But before we get to the code, let's see how you would conceptually solve this problem, right? So let's say that the input number n was 19. So we want to turn 19 into binary. So how would we do this? Well, imagine that this input is some weight, okay? That you've put on a scale, and you want to balance on the other side using weights that are powers of 2. So here what you're seeing are weights that I have in my possession, which are all powers of 2. So this is 2 to the power 2, 2 to the power 1, 2 to the power 0, 2 to the power 1, 2 to the power 2, 2 to the power 3, and 2 to the power 4, right? Now I don't need to go beyond 16 because my weight here is 19. Okay, so the largest power of 2 that I need to consider in this case is simply 16. Okay, so I have my weights, which are powers of 2, and I want to use these guys to balance 19. So how would I do it? Well, what's the largest power of 2 that I need to consider for this to balance this guy? Well, I take 16, right? So that's what we see here. And when I do that, I put a 1 for that to record the fact that I considered the weight 16. Okay. Now, if I put a 16 here, how much am I left with to balance? Well, it's 19 minus 16, which is 3. Okay. Now, do I need to consider this weight 8? No, because that exceeds 3. Right? So in that case, I put a 0, saying that I'm not including the weight 8 on the right hand side. Okay? What about the number 4? Well, 4, we don't need 4 either because that exceeds 3. So I put a 0 for that. But what about 2? Well, 2 is less than 3, so I consider it, so I put a 1 for it. And when I do that, I have a 16 and a 2. What's the total? It's 18. I'm one short. 19 minus 18 is 1. And then I have this weight that I use to balance the whole thing up. Okay, so now I have 19 on the right hand side. And since I considered this weight, I put a 1 for it. Now what is this guy here? Well, this is the binary representation for 19, because what we have here is 1 times 2 to the power 4 plus 0 times 2 to the power 3 plus 0 times 2 to the power 2 plus 1 times 2 to the power 1 plus 1 times 2 to the power 0. So this is basically 16 plus 0 plus 0 plus 2 plus 1, and that is 19. right? So that's how you would solve the problems conceptually, and the Python program that you see here exactly mimics this idea. It implements this idea. Okay, it translates this idea into Python code. So let's see how it works. We import our usual modules sys and stdio, and then we read a single command line argument n as an integer. So we are interested in turning that number into binary. And then we initialize a variable called v to the value 1. And then we have this while loop that says as long as v is less than or equal to n integer division 2, we say the new value for v is twice the current value. So what this loop is doing is it's identifying the largest value of v that is less than or equal to n. So largest value of v which is less than or equal to n. So for example, if n is 19, right, which was the input here, this while loop will correctly identify v to be 16, right? So let's see how it does that. So if n is 19, then what is n star star 2? So 19 slash slash 2 is what? Is simply 10, right? So that's the integer division of 19 and 2. Now, is v, which is currently 1, less than or equal to 10? Well, it is. So v is calculated as twice the current value, which is 1. So new value for v is 2. Okay, and then we perform this check again. Is 2 less than or equal to 10? It is. So the new value of v becomes 4. Now, is v less than or is 4 less than or equal to 10? It is. So the new value for v becomes 8, right? So the current value times 2, and then this is still less than or equal to 10, so the new value becomes 16. But now 16 is not less than or equal to 10. Okay, so you're out of the loop, and the value that you have for v is 16, which is the largest power of 2 that evenly that's less than or equal to 19. Right? Okay, so now let's see how the next while loop works. So here we check as long as v, which was identified here by the first while loop, as long as that value is strictly greater than 0, what we do is we check if v is greater than n or not, meaning and n at this point is what you have left to be balanced. Okay, initially it was 19, v was identified to be 16. Is 16 greater than 19? No, it's not. So what we do is we come here and we print 1, okay, without a new line character. And what we're saying is that we considered the weight 16 because it was less than 19. Okay, so we print 1. So it's like what we did here. We included 16. And then what we do is, since we included 16, we take 16 out from 19. So the current value of n minus v becomes the new value of n. So n now becomes 19 minus 16, which is 3. Okay, so n is now 3. And then what we do is we say v slash slash equals 2. So this is the same thing as saying v equals v slash slash 2. So we cut the weight, we cut the value of v by 2. So v was 16, the new value is now 8. So we're basically looking at the next weight, and we are seeing if that needs to be included or not. Well, 8 is still greater than 0, so we are inside the while loop. Now v is 8, n is 3, but 8 is greater than 3, so this condition is true. So we end up writing 0. So what we are saying is we don't need to include the weight 8, right? And then what happens is v becomes 4, so that's the next weight. Now 4 is greater than 0, so we are still in the while loop. Is 4 greater than 3? It is, so we write 0. and we cut the value of v by half. So v now is 2. Is 2 greater than 0? Yes. Is 2 greater than 3? It's not. So we end up here and we write 1. Okay. And now we take 2 away from 3 and store the result back into n. So the new value for n now is just 1. Right? So n is now 1. And then v is cut down further by 2. So v now is 1. Now, is 1 greater than 0? Yes. Is 1 greater than 1? No, it's not. So this expression is false. We end up here and we write 1. So that's how we get this one. Right? And then we cut n by v. So v was now 1, n was 1, so n now becomes 0, meaning we have balanced the weight. And then v itself becomes 0 because it is 1 integer division 2, which is 0. Okay, and now when we come here, v is 0, so it's not greater than 0, so you're outside the while loop and you end up printing a new line character. Okay, so for this particular input n equals 19, we see the output 1 0 0 1 1 new line character. Okay, so the prompt is going to be on the new line. Okay, so here we run the program with n equals 19. The program comes back with exactly this output 1 0 0 1 1. We run it with 255. The program comes back with this as the binary representation. Then we run it with 512. It comes back with that. Run it with that. It comes back with that. So the program correctly computes and prints the binary representation of an input number n. Okay, so the next application that we're going to consider is called gambler.py, and what it does is it accepts an integer command line argument. It accepts 3 command line arguments, all integers, and these are called stake, goal, and trials. And then the program performs trials number of experiments. Okay, and I'll explain what an experiment is. And each experiment is as follows. So you have a gambler that has in her possession stake number of dollars. All right. And then what this gambler is going to do is in each experiment, the gambler is going to place a fair $1 bet. All right. And that experiment is going to terminate either when the gambler has achieved the goal, or if the gambler goes bankrupt, meaning ends up with $0 in her possession. Okay, so let me repeat. So each experiment involves the gambler starting with stake dollars and placing $1 bets and stopping when either the goal is achieved or if the gambler goes bankrupt, meaning has no money left. Okay, and then we perform the next experiment, which is basically repeating the same process. Okay, and we do this trials number of times, so that's the number of experiments that we perform. And for output, what we do is we write the percentage of wins, meaning out of these many experiments, how many times did the gambler starting from stake reach the goal? And we also print the average number of bets per experiment, right? So in each experiment, how many bets were placed on average? So that's what the program does, right? Okay. So here in this picture, you see 2 scenarios. In the first case, the gambler starts with these many dollars and has set a goal of these many dollars, and the gambler constantly places $1 bets. Right? Sometimes she loses, sometimes wins, and so on. Sometimes loses, wins, loses, and so on. So in this particular scenario, the gambler at some point achieves the goal. So this is a winning scenario. Right? And here's another scenario where the gambler starts with these many dollars, has that for the goal, and wins, and then loses, and so on, wins, loses, and loses. Okay, and at some point ends up with $0. So this is an example of a losing scenario. Okay, so that's what each experiment involves. Starting with these many dollars and stopping either when the goal is achieved, which is a win, or when the gambler goes bankrupt, which is a loss. Okay, so let's see how this program is implemented. Now, since we are simulating a random process, we import random and then we import the usual modules std, io, and sys. We receive 3 command line arguments: stake, goal, and trials. And then we initialize 2 variables, bets to 0 and wins to 0. So bets is going to keep track of the number of bets placed total, and wins is going to keep track of how many times out of trials did the gambler win. Okay, meaning ended up reaching the goal. Okay, so we have an outer for loop where t goes from 0 all the way up to trials minus 1. Notice that we are calling range with 1 argument. When you do that, that is basically the stop, and the progression that you get in that case is 0, 1, 2, and so on, all the way up to trials minus 1. Right? So that's the outer loop. And then what we have here is the body of the for loop is one experiment of the gambler starting at stake. So we set a variable called cash to stake. So the gambler starts with that much money. And then what we do is we have this while loop that says as long as the gambler has some money left, so cash greater than 0, and the gambler hasn't reached the goal yet. Okay, so the gambler is not bankrupt and hasn't reached the goal yet, then the gambler is going to place a bet. So increment the bets variable by 1, so a new bet. And then how do we simulate a bet? Well, it's a fair bet. So what we do is we simply flip a coin. So if you remember our first program that we saw in this section, flip.py, this is exactly what we did there. So this Boolean expression is basically simulating a coin flip, right? A fair coin flip. So if this is true, then we say that the gambler won that bet, so we increment cash by 1. Okay, the number of dollars that the gambler currently has incremented by 1 because she won the bet. But what if this was false? Well, in that case, we say the gambler lost the bet, so we decrement cash by 1, right? So that's the idea. And then we do this as long as the gambler still has some money left and hasn't reached the goal. Okay. Now, if this Boolean expression is false, then one of 2 things has to be true, meaning the gambler has either gone bankrupt or the gambler has reached the goal. So when we are outside the while loop, what we do is we simply check which scenario was it. Did the gambler actually reach the goal? Meaning, is cash, the current cash that the gambler has, is it goal? In that case, we say it was a win. Okay, so we increment wins by 1. Otherwise, if this condition is not true, it means that the gambler in this particular experiment went bankrupt. Okay, in which case we do not increment wins by 1. Okay, so all of that is one experiment, and we repeat this exactly trials number of times, which is what is controlled by this outer for loop. Okay, and once the trials number of experiments is done, we are outside of the for loop, and the first thing that we do is we print this part, the percentage of wins. Okay, so we simply take the value of wins divided by trials, notice the integer division, multiplied by 100, okay, and report that as the percentage of bets. And then what we do is we print the average number of bets, which is simply the total number of bets, integer division, the total number of trials. Okay, so that's how we print the output. So here are a couple of runs of the program. We first run it with that for stake, that for goal, and that for trials. So 100 experiments where each experiment involve the gambler starting with $50 and setting a goal of $250. And for output, what we see is that the gambler won about 25% of the time and placed these many bets on average. Okay, and in the second run, we run 100 experiments where in each experiment the gambler starts with $500 and sets a personal goal of $2,500. And in this case, we notice that the gambler won about 27% of the time, and the average number of bets was about that. Now, in this problem, it turns out that the two quantities that we are interested in can actually be mathematically calculated. Okay, so the percentage of wins has this very nice formula. Okay, and then the average number of bets has this nice formula. Okay, so this is one of those problems that can be addressed mathematically. Okay, so it's amenable to mathematical analysis. Not all problems sort of lend themselves for mathematical analysis, but this is an example of a scenario where we can actually carry out mathematical analysis and figure things out. Okay, so here we are not only able to do it mathematically, but we can also do it computationally, which is what we are doing here using this Python program, and we can compare the results. So what we can do, for example, is plug in these values for the inside these formulae and see if we get comparable results. So let's check it out. So here stake was 50 and goal was 250. So what we have is, for percentage wins, the formula says it is 100 times 50 divided by 250. So this is 5 and this is about 20. Okay. Right. So this is about 20, and that's roughly what we see. 24%. Of course, we're not from the program. We're not going to get exactly the same number, because this is, after all, a random process, right? That the program is simulating. What about the average number of bets? Well, the formula says it is stake times goal minus stake. Well, the stake was 50, and goal minus stake is 250 minus 50, which is 50 times 200, and that is 10,000. And what we get here from the program is 12,000 something. So it is pretty close to 10,000, right? Again, we're not going to get exactly the same numbers because the program is simulating a random process, but it's pretty close. And it's kind of nice that, the results that you get computationally is comparable to what you get from mathematical analysis. But we have to keep in mind that very few, real world problems are mathematically tractable. Right? In some cases, you just have to rely on computational means to get a handle on the problem. But here we just got lucky. This program can also be analyzed mathematically. Right? Our last application is going to be this program, which is called factors.py. And what this program does is it accepts a command line argument n as an integer, and it simply writes out the prime factors of n, right? So for example, if n is 4, it's going to write out 2 and 2 because those are the prime factors of 4. If n is 6, it's going to write 2 and 3 because 2 times 3 is 6, right? And so on. And if you give it a prime number such as 11, it's simply going to write 11 out because it doesn't have any prime factors other than 1 and itself. Okay, so that's what the program does. So let's see how it works. We import our usual modules, and then we get a command line argument n as an integer. And then we initialize factor to the number 2, right? And then we have nested while loops. In the outer loop, we check if factor time factor is less than or equal to n, which is the same thing as saying factor less than or equal to square root of n, right? It means the same thing. Okay, and if that is true, then we have another while loop where we check if factor evenly divides n or not. So this condition here checks if n is evenly divisible by factor. Okay, and if so, what we do is, so if this condition is true, we cut n by factor. Okay, and we simply write factor out because we just identified a factor of the number n, so we write it out. Okay, and then we keep repeating this while loop until this condition is true. So for as long as this condition is true, we keep cutting n by factor and writing the factor out. But when this condition turns out to be false, then what we do is we look at the next factor. Okay, so we increment factor by 1 and then we repeat the outer loop. So if this condition is still true, then we perform the inner loop again, and so on and so on and so on. Okay, so this inner loop basically what it does is it looks for a particular factor of a number, and it also checks if it's a repeated factor. So for example, when n was 2, right, its prime factors was 2, and that was repeated, right? That's what this loop does. And then here we look, we update the factor by 1 and check all over again, right? Okay, and then when this condition is false, which happens precisely when factor times factor is strictly greater than n, what we do is outside the outer while loop, we simply check if n is strictly greater than 1, and if so, we write the value of n and then write a new line character after it. All right? So that's how this program works. That's how it breaks down a given number into its prime factors. So let's take a concrete example. Let's take n equals 4 and see how it's broken into its prime factors, which we know are 2 and 2. Right? So n is 4, factor starts at 2. Now, is 2 times 2 less than or equal to 4? Yes, so this condition is true. So we go in here and we check if 4 is evenly divisible by 2. Well, it is. So what we do is we cut n down by factor. So the new value for n now is 2. And we write factor out with a space. So we write 2 space. Right? And then we go back and check if the current value of n, which is 2, is evenly divisible by 2. Well, it is. So what we do is we cut n by 2 again. So so now n becomes 1. And we write factor out, which was still 2, so 2 space. Okay, and then we check if the current value of n, which is 1, is evenly divisible by 2. Well, it's not, so we are outside the inner while loop, and we end up here, and factor now becomes 3. Okay, and then we check, is 3 times 3, which is 9, less than or equal to the current value of n, which is 1? No, so that Boolean expression becomes false, and we end up here. Right? Is 1 greater than 1? No, so this is not true either. So we end up writing a new line character. So the output when n is 4 is simply 2 space 2 space and the new line character. So the prompt is on a new line. Okay, so the program is correctly printed out the prime factors of 4 as 2 and 2. Let's take another example. Let's take n equals 6. Okay. So n is a 6, factor starts at 2, so is 2 times 2 less than or equal to 6? Yes. Then we check, is 6 evenly divisible by 2? Yes. So we cut n by 2, so n now becomes 3. And we print factor out, which is 2 space. And then we go and check, is 3, which is the current value of n, evenly divisible by 2? Well, it's not, so you're outside the inner while loop, and factor now becomes the next value, which is 3. And then we check here, is 3 times 3 less than or equal to the current value of n, which is 3? So is 9 less than or equal to 3? It's not, so you're outside this while loop, and you end up here. n, which is now at a 3, is it strictly greater than 1? Yes, it is. So in that case, we end up writing n. So we end up writing 3 and the new line character from here, right? And we end up with the prompt on the next line. So when n is 6, the program correctly prints its prime factors as 2 and 3. Okay. So here's here are a couple of runs of the program with different values for n. So we give it a rather large number, and the program comes back with these as the prime factors. We give it a much bigger number than that, and the program comes back with these numbers as the prime factors. So what we are saying is that this number here is basically that times that times that. So all these guys are prime numbers. Okay, so their product is this large number. Okay. Now this program is very interesting and very important. Okay, so it basically takes a number and breaks it down into its prime factors. Now, though we are able to do it, it doesn't mean that this program is efficient, meaning that it will be able to take an arbitrarily large number and break it into its prime factors efficiently, right? And it turns out that that problem cannot be done efficiently, right? So you cannot take an arbitrarily large number and break it into its prime factors easily or efficiently. Okay, and that's a good thing, because modern crypto systems, they rely on not being able to factor large numbers. Okay, because the way these crypto systems are implemented are using large numbers, which are products of huge prime numbers. So if someone is able to write a program that can break these large numbers into their constituent primes, then they can very easily crack into the crypto code, right? So it's actually a very good thing that this problem is not efficiently solvable. Okay. So the last bit for this section is just talking about some other conditional and loop constructs. Now, there is a construct called the conditional expression, which is shown here, and that provides an alternate form of an if-else statement. Okay, but the conditional expression syntax is basically an expression. So this whole thing is an expression, right? It's not a statement. So you cannot have this as a line of code in itself, but you can use it wherever you need an expression. So the whole thing is an expression, and the way it works is as follows. So the whole expression evaluates to this guy, so it collapses to this particular expression if this Boolean expression is true. Okay, and it collapses to this particular expression when this Boolean expression is false. Okay, so as you can see, you can use it as an alternate form of an if-else statement. So if this Boolean expression is true, the whole expression collapses to that. If this Boolean expression is false, the whole expression collapses to that. Right? Let me give you an example of this. So here is a conditional expression, okay, which collapses to heads if this Boolean expression is true. So meaning if you get a random number that is less than 0.5, flip is assigned the value heads. But if this is false, meaning if random.random gave me a value that was greater than or equal to 0.5, then this expression is false, in which case flip is assigned tails, right? So in what I've done here is I'm setting flip to either heads or tails depending on a coin flip, which is what is simulated by this expression. Okay, so it's a nice little application of the conditional expression syntax. But again, remember that the conditional expression is an expression. Okay, so you can use it wherever you need an expression, but it cannot be used as a line of code in itself. In other words, you cannot use it as a statement. All right. Now a break statement is something that immediately exits a loop without letting it to run to completion. So if you want to prematurely terminate a loop, it's the break statement that you would use. So here is an example of that. And this code tests if a given number n is prime or not. Okay. So we first set I to 0, and as long as I is less than or equal to n divided by I, so this thing is saying I less than or equal to square root of n. So as long as this is true, we test if I evenly divides n or not. Okay, and if so, we know right away that n is not a prime number because we have found a number that evenly divides n. Okay? So in that case, there is no point in continuing this loop, so we break. So the way break will work then is it will simply exit the loop, right? So if we find an I that evenly divides n, we prematurely exit the loop and you end up here. Otherwise, we increment the value of I by 1 and check if that value of I evenly divides n or not. Okay, we'll repeat the process as long as I is less than or equal to square root of n. Okay? And when I takes on a value that is strictly greater than the square root of n, you're outside the while loop. Okay. Now the question is, when you get here to this point, how did we get here? Well, there are two possible ways in which you could have gotten here. You could have come here either prematurely via this break, or you could have come here by exhausting the loop, which is precisely when I is greater than or equal to greater than square root of n. Okay. Now, so the thing is, when is n prime then? Well, when you got here prematurely via the break, right, then you know that n is a prime number. N is not a prime number because that happened when I evenly divides n, right? But if you get here by exhausting the loop, which is when I is strictly greater than square root of n, you know that you didn't find any proper divisor of n at all, so n is a prime number. So to conclude whether or not n is prime, what we do is we use this conditional expression syntax and check if I at this point is strictly greater than n over I. If this is true, it means that the loop was exhausted. The loop was exhausted and the number is prime. Okay? But if this is false, then it would mean that we got here prematurely by finding an I that evenly divided n. So let me say, so this would mean true. And if it is false, that would mean that premature exit. So we exited the loop prematurely and the number is not a prime. Okay, and that's exactly what we are doing here. So read this. So let's see. So if this is true, then this whole conditional expression, that you see in parenthesis, if this is true, collapses to that. Okay, and what are we printing? We are printing n is prime, right? When this is true. Okay, but when this expression is false, then this conditional expression collapses to that, in which case we are printing n is not prime. Okay. So it's a very nice example that shows how you work with the break statement, and it's also a good illustration of how you make use of the conditional expression. Right. All right, and then there is a statement form called the continue statement that skips to the next iteration of a loop. So this is sort of like the opposite of break. So when continue statement is executed, it skips whatever follows continue statement and performs the next iteration of the loop. Okay? So here is a nice example of that. So in this code, what we are doing is we are simply iterating over the characters of the English alphabet. Okay? So remember that a string is iterable, so I can put that here in a for loop and iterate over its characters using this variable c. So in the first iteration c is going to be b, in the second iteration, in the first iteration is going to be a, second iteration b, and so on, and in the last iteration it's going to be z. And inside, what I'm doing is I'm checking if C is one of these 5 characters, A, E, I, O, or U. And if so, I simply continue. So in which case, I don't write the character. Okay. But if it is a character other than these 5 characters, I write it. So what is this code doing? It's simply iterating over the characters of the English alphabet, and it is printing just the consonants and not the vowels. Because if we see a character that's a vowel, we continue. But if it's a consonant, we print it. Okay, so it's a nice example that shows how you make use of the continue statement to skip to the next iteration of a loop. Okay, so with that, we are done with this section on control flow. Thanks for watching.